In this session, we're going to talk about the quantum mechanical model of atoms. So we're going to talk about the shells, the subshells, the capacity of these subshells and the shell capacity itself. Now we're going to achieve this by using what we call AUFBAU'S principle. We're going to achieve this by using what we call HUND'S rule. Then we're also going to talk about electronic configuration, how you show them in terms of orbitals. Okay. So let's start. So we're talking about shells. Okay, now you know that the shells, in an atom, the shells, let's say this is the nucleus. In the shells, that's where you find your electrons, like that. And the electrons are the ones that are involved in the reaction, especially the valence electrons, the electrons in the outermost shell. So in this case, we're talking about a shell. Now, where exactly are you going to find the electrons on a shell? Okay, you're going to find them in subshells. Now, in those subshells, where exactly? You're going to find them in what we call orbitals, right? Okay, orbitals. Now, an orbital is just, the place on an atom where there is a likely probability of finding an electron. Okay, now let's talk about, the capacity of these shells in terms of how they hold these, electrons. So we'll start from the shells, then let's talk about what we call the subshell. Okay, then we can also talk about the subshell capacity. Then also the shell capacity overall. The shell capacity. Okay, let's say you have shells number let's say you have shells number 1, you have shell number 2, you have shell number 3, and you have shell number 4. Now, you know that the subshells that we have, there's an S subshell, there is a P subshell, there is a D subshell, there is an F subshell. Okay, so these are some of the shells that you're going to have. Now, the subshells that you're going to have. Okay, so now let's talk about these subshells. So in shell number 1, or in the first shell, you only have the S subshell. Okay, the S subshell. In shell number 2, you're going to have the S subshell and the P subshell. Okay, then in shell number 3, you're going to have the S, the P, and the D subshell. Then in shell number 4, you're going to have S, P, D, and F subshell. Okay, let's just illustrate this one. So in shell number 1, you only have the S. In shell number 2, you have the S and the P. In shell number 3, you have the S, the P, and the D. In shell number 4, you have the S, the P, the D, and the F. Okay, now let's talk about the capacity of these subshells. So the maximum, number of electrons the S subshell can have is 2. Let's indicate that. Then the maximum number of capacity the second shell can have is 2 first in S, then 6 in P. P has PX, it has PY, and a PZ, and each has a capacity of holding 2 electrons. So overall, the P subshell will hold 6 electrons. Okay, so that's the second shell. Then let's talk about the third shell. In the third shell, so the S will have 2, the P, like we earlier said, is supposed to be 6, then the D has 10. Okay, then let's also talk about the last one. So the S is 2, the P is 6, okay, the D is 10, then the F is is 14, like that. Okay, let's indicate them. Okay, just a recap. So the S has a maximum, has a capacity of the S sharp shell has a capacity of 2, and is 2. Okay, and like that. Okay, the S is 2, the P is 6, the D is 10. The S is 2, the P is 6, the D is 10, the F is 14. Okay, now let's now talk about now the overall shell capacity. Okay, so let's start with our shell number 1. Okay, so how many electrons is it supposed to have? This is the S subshell. So you're going to realize that we only have 2 here, so it has a capacity of having 2 electrons. Okay, so the maximum is 2. Okay, then in the second subshell, subshell we've got S, and P. S has 2 and P has 6. So when we add the 2, what are we going to get? So we're going to get 2 plus 6, that is just your 8, like that. Okay, like that. Okay, then in the third one, what are we going to have? Okay, so we've got 2, we've got 6, and we've got 3. So 2 plus 6, that is 8. 8 plus 10, that is 18. So the maximum that your third shell can have is 18. Okay, like that. Okay, now let's talk about the last one, the fourth shell. What's the shell capacity in terms of electrons? So you have 2, you have 6, you have 10, and you also have and 14. Okay, so we add 2 plus 6, that is 8. 8 plus 10, that is 18. 18 plus 14, that is a 32. Okay, so you must understand that the maximum amount of electrons, or number of electrons a subshell can hold is 2. The maximum a P can hold is 3. The maximum a D can hold is 10. The maximum an F can hold is 14. Okay, now the maximum number of electrons the first shell can hold is 2. The second one is 8. The third one is 18, and the fourth one is 32. Okay, let's talk about this shells one by one. Okay, so a subshell. So we said we've got an S, we've got a P, we've got a D, and we've got an F. Okay, so these ones are called subshells, like we earlier said. Okay, now the subshell defines the shape of a particular orbital. The ace has its own a shape. Now a subshell is composed of one or more orbitals, and an orbital is the region or space where there is the highest probability of finding a particular electron, like we said. So each orbital, let me represent an orbital in terms maybe of a box, like that. Each orbital has a maximum, or each orbital can hold 2 electrons, and let's represent electrons as arrows. Okay, 2 electrons. Each orbital has that capacity. So the S orbital, or the S subshell, has 1 orbital. Okay, so because it has 1 orbital, the maximum number of electrons that it can hold is 2. So 2 electrons. Okay, then we've got a P, the P subshell. We've said that the maximum, or let me say, it has 3 orbitals. That's what we say, it has 3 orbitals. Okay, let's represent them like this. Okay. Let's say these are orbitals, like that. Okay, let's draw them like that, 3 of them. Okay, so we are saying it has 3 orbitals. So it means the maximum number of electrons that it can hold is 1, 2, okay. So you realize that it can only hold about 6 electrons. Okay, so that's what we earlier said. Then for the d orbital, it has 5 orbitals. The d subshell has 5 orbitals, so it means the maximum number of electrons that it can hold again is 10 electrons, like that. Then for the f1, the f, it has 7 orbitals. Okay, 7 orbitals, like that. Okay, so I just wanted to illustrate this point. Then we've got what we call the AUFBAU'S principle. Now the AUFBAU'S principle states that electrons will go into the shells and the subshells of the lowest energy. Okay, so you know that the S will be the one that is the lowest in energy. Okay, so you have to understand that. So now a shell is denoted by the principal quantum number, the subshell, and the number of electrons in the subshell. Let's give an example. If let's say you have 3 electrons, electrons in the p subshell. In the p, let's say subshell. Now of the fourth shell. So now how can you show this in terms of a representation? So an expression will be, you are saying the principal quantum number is 4, right? And these electrons are found in the p subshell. And how many are they? We are saying there are 3 electrons. So this is how you're going to illustrate this. So your 4 in this case is what we call your principal quantum number, like that. Okay, then your p in this case, we're saying this is just our subshell p. Okay, then your 3 in this case, this is just the number of electrons. Okay, the number of electrons in the subshell, your superscript, like that. So this is what you are going to show. So we always begin with the ground state of 1 electron, so which has an A's subshell. Now let's talk about the electronic configuration of most of these elements. Let's start from the first element, which is hydrogen. Okay, so we're talking about configurations or electronic configurations. Okay, so we're saying you always start from the ground state. Okay, so let's start with the electronic configuration for hydrogen. Hydrogen is H. Okay, so how are you going to represent the electronic configuration? So we are saying the first shell is 1, right? Okay, let's start with the first shell. In the first shell, what are you going to have? You are going to have the S, the S subshell. And hydrogen, it being number 1, it has an atomic number of 1. So the electrons, the number of electrons is equal to the number of protons. So in this case, the number of electrons will be just 1, like that. So it will be 1s1. How do you show this in an orbital? So you draw your orbital. Okay, then you show your arrow like that. Okay, to show that this is an electron. So this is just 1s, like that. Okay, let's talk about another one. The second one is helium. Helium is denoted as so helium, it being number 2. So we're going to have 1. This is the phase subshell, and this is the subshell. So it will have 2 electrons, right? We said the maximum number of electrons that the S shell can hold is 2. So I'm going to show that in an orbital. So you are going to draw your orbital. we're saying you have 2 electrons, so 1 points upwards, 1 points downwards. Okay, then what about the third one, lithium? Okay, lithium. How are we going to show lithium? So the S sharp shell, it has a capacity of 2. Now that the S, we were saying this one has 3. So now what about the last electron? So the last electron will go into the second subshell. In the second subshell, you're going to find S and P. So the S shell, the second shell has 2 subshells, the S and the P, but the lower in energy is the S subshell. So it fuse first. So you have 2S, 1 like that. Okay. Then in terms of representation, how are we going to draw this? Okay. So this will be your S, your first, So this will be 1 electron, the second one. Then we said the third one will go in the 2S like that. Okay. So you're just going to have that like that, an arrow like that. So we're saying this is your 1S, your 1S. Then this is S2. Then this is just your 2S like that. Okay. Let's also represent beryllium. Okay, beryllium, which is Be. So it is number 4. So I find that the S will fill first, then your 2S like that. The second the second subshell like that. So now what are you going to have? So all of them will just be filled like that. This is the first, this is the second. Okay, so this one fills, you come to the next one, this one fills like that. Okay, let's also talk about boron. Now how are we going to represent boron? Boron is number 5. So let me it's number 5, so it has 5 electrons. So our B in this case will be your 1S. Your S will have 2 electrons. You go in the 2S, this will also have 2 electrons. Now we said the second subshell, it can accommodate, it has the S and the S and the P. So now the first 2 are filled. So what are you going to have? The other one will go into the 2p. Okay, it will go into the 2p. Okay, so this will be the electronic configuration. In terms of an orbital, illustration, you're going to do that. Let's say these are our orbitals, where we find our electrons like that. So this will be the first electron, this will be the first, your S, your S subshell. Then you're going to the 2, so this is will be our 2S. Then this will be just our 2p with 1 electron like that. Okay, so now that we've talked about how you represent these electrons, let's talk about the Pauli's exclusion principle in a more comprehensive manner. So like we earlier said, the Pauli's exclusion principle just states that in a given atom, no 2 electrons can have the same set of 4 quantum numbers. Now the quantum numbers that we're talking about here, you've got what we call the N, you've got what we call the L, you've got what we call the M2. Okay, you've got what we call the MS like that. Now the N in this case, this one is the principal quantum number. Then your L in this case, this is the angular momentum. Quantum number. Then you've got the M2. The M2 in this case to represent the magnetic quantum number. Okay, then your ms, this is just your spin, or the electron spin. So this is the electron, electron spin, quantum number, like that. Okay, so now let's represent this in overall. So what are you going to have? So in the first shell we said you are supposed to have the 1s, right? Then when the s is completely filled, you are going to have the 2s. Okay, 2s. Then after that you go to your 2p. Okay, these are the the subshells that are found. This is our shell number 1, this is our shell number 2. Then in the third shell we said you have the s, so this would be 3p, this would be 3d. We said in the third shell you have 3 subshells, sp, spd. In the fourth subshell, so this would be 4s, 4p, 4d, and 4f. Okay, then in the fifth, you've got s, you've got 5p, you've got 5d, you've got 5f. Then in the sixth subshell you have 6s, you have 6p, you have 6d. Okay, then in the last one, let's say in the seventh shell you have 7s, you have 7p. Okay, so this is how now you you fill the orbitals. So we said you start first with the first s, so your 1s, so this must be filled first. Then you go to your 2s, then from your 2s you go to your 2p, then you go to your 3s. Okay, then from your 3s you're going to go to your 3p, and you go to your 4s. From your 4s you go to your 3d, 4p, 5s. Then from your 4d, from your 5s you're going to go to your 4d, 5p, 6s. Okay, then from your your 6s you're going to go to your 4f, 5d, 6p, and 7s, like that. Then the last one will be from your 5f to your 6p, like that. So this is how you arrange these electrons. So if you follow this, it will be very easy in terms of allocating your electrons. Now let's talk about what we call HUND'S rule. HUND'S rule. Now what is HUND'S rule? Now HUND'S rule states that electrons occupy separate orbitals in the same subshell with parallel spins. So you find that let's say these are our orbitals. So electrons occupy separate orbitals in the same subshell. Let's pick maybe the p subshell, okay, which has three components. There's the p, the px, the py, the pz. Okay, so electrons will occupy separate orbitals in the same shell with parallel spins. Okay, so let's say your first electron will be there, the second electron will be there, but this is in the same subshell. Since electrons have the same charge, they repel each other to different regions of space. Electrons want their space, so they prefer separate orbitals rather than pairing in the same orbital. So pairing only occurs when separate empty orbitals in the same subshell are not available. So okay, with the HUND'S rule, let's draw some diagrams to put this into context. Okay, let's do with we've talked about, we ended on boron. Okay, now let's talk about carbon, let's talk about nitrogen, let's talk about oxygen, let's also talk about fluorine, probably even a neon, like that. Okay, let's start with carbon. How are you going to represent it? So let's say this is carbon has how many electrons? It has 6 electrons. Okay, so let's say these are our orbitals like that. Okay, so in the first shell we're going to have 2, right? When these ones are filled, we go to the second shell, so you have 2 electrons. Now we are remaining with 2 electrons. So let's say this is our 1s, this is our 2s, then this is our 2p. Okay, so we've already filled our 2s. Now we want to fill the last 2 in the last subshell. So what are we going to do? So instead of putting all of them in the first box, the other one also will have its own space. So why is it that? Because electrons, if other subshells are empty, they'd rather be in those areas to avoid like, because of their repulsion, they prefer their own space. So that's what we're talking about. So if you're going to show nitrogen, how are you going to show nitrogen? Okay, how many electrons does nitrogen have? 7. Okay, 7. So how are we going to represent it? Let's say these are our orbitals. Okay, so how are we now going to show them? So that the first subshell only accommodates 2 electrons. You go to your second subshell, so these will also fill. Okay, we are remaining with 3 more electrons. So instead of us having 2 and 1 and leaving this blank, we are going to use HUND'S rule. So in this case, they'll all be in the separate orbitals like that, because we said they prefer their own space. Okay, now let's show oxygen. Now how are we going to show oxygen? Okay, oxygen has 8 electrons. Okay, let's say this is the second subshell. This is the second subshell for the P. Okay, so for oxygen, how are we going to represent? So the first 2, they'll fill in the first subshell, which is 1s. Then the second 2 will go now to your 2s. So your 2s will fill. Now you're going to your 2p. So we are remaining with how many? We're saying oxygen is number 8. So you're remaining with 4 more electrons. So the first 3 will fill. Now you're remaining with 1. So the other one now will come there. Okay, you come there like that. So now you have 4 like that. Okay, let's also show for the other ones. We said fluorine. Okay, fluorine. Okay, fluorine has how many electrons? Fluorine is number 9, right? Okay, so we're going to draw. Let's say this is our S. This is our 2S. Let's say this is our 2P. Okay, now how are we going to draw? So the first 2 will fill. Okay, now we're going to the 2s, so the 2s will also fill. Now we go to the 2p. So what are we going to do? So let the first ones fill. Okay, now we're remaining with 2, so they will now come and fill like that. Okay, so that is for fluorine. What about neon? Neon is one of those stable gases. So what are you going to have? Let's say this is our our S like that. This is our 2s. let's say this is our 2p like that. So how are we going to represent? So the first one, fuse. Okay, we come to the 2s, the 2s fuse. Okay, we come to the 2p. Okay, so what are you going to have? So they'll few. Now we're remaining with 3 electrons, so they'll also few sequentially like that. Okay, so this is how we represent the electronic configurations for these atoms when you when you want to represent them in orbitals, and just to write them using the HUND'S rule and the Pauli's exclusion principle. Thank you for watching, and don't forget to subscribe to our channel. See you in our next video.